Hey guys, thanks for coming back. Okay, I'm just going to answer, for this video, I'm just going to answer the bonus question that I posed to you guys at the end of the geometric probability video, and that was this. So we're going to answer this question. It was intended to be a little bit more difficult than the questions we'd been doing, but not too terribly so much so. Here's what the question was. Imagine that you have a coin and the coin is unfair. So you're going to be flipping the coin and using it to answer these geometric probability questions. And the coin is set up such that, in this funny way, it's kind of an unfair coin. The probability of heads, here's how it's set up. The probability of heads is equal to 2 times the probability of tails. Remember, tails we can think of as heads complement. So we know that about the coin, and that's part of the premise. The actual question itself is this. What is the probability that the first success, which we're defining as the first heads, the first success, x, would occur on or after the 4th trial? So we're going to have to figure that out. The first thing we ought to do, I guess, there's a number of ways we can start. We can analyze the sample space, but I'm going to do that next. Right now, let's just get the probability distribution of this coin out of the way. So here's what it looks like. The probability of heads is equal to 2 times the probability of tails. Well, we know that any event and its complement, and there's really in the sample space of what can happen when you flip a coin, there's really only 2 events that are reasonable for us to consider in the sample space, and that is heads and tails. Tails we can think of as heads complement. We could think of heads as tails complement in another setting too. Either way, for now we're going to look at it this way. We know that the sum of these 2 probabilities must equal to 1 because they are the sample space. We also know that the probability of heads is equal to 2 times the probability of tails. So you know what? I'm just going to do a little algebra. And I'm going to plug that in. It's a little messy, but I think we can read it. The probability of heads being 2 times the probability of tails plus the probability of tails still has to equal 1. If this is true, then this must be true based on our premise. Well, that's 3 times the probability of tails. And if I divide both sides of this equation by 3, I have that the probability of tails must equal 1/3. I'm just going to go out on a limb here and guess that a bunch of you guys kind of saw that intuitively. You may also have thought that you saw the answer to this intuitively and may have gone in the wrong direction. That happens. So that's one of the reasons why I'm always trying to tell my students, look, even if you think you know where it's going, it's safer and probably not that much slower just to be careful and run through it and make sure you didn't make a mistake. I'm assuming I didn't. You guys will let me know if I did. The probability of tails is 1/3. We know very well, moving on to the next part of this. Let me write that down. We know very well that the probability of tails is 1/3 and that we can think of the probability of heads as being the complement of the probability of tails. So you know what? I'm going to utilize the complement rule again and say the probability of heads is 1 minus the probability of tails because they are complementary. And that means the probability of heads must be 1 minus 1/3, which is 2/3. Okay, awesome. So we have our probability distribution. Let me put that up here. The probability of heads, and I don't want to run out of space, is equal to 2/3. Good. Now we have this part of the question, and this is going to be very similar to a couple of the things that we did in the geometric probability distribution video, but let's just run over it again. If we're looking at the sample space of how many times can we flip this coin and get our first success, the sample space is going to look like this. We might get our first success on the 1st trial, on the 2nd trial, on the 3rd trial, on the 4th trial, and so on, all the way through infinity. That's the way the geometric probability distribution works. And we're being asked, what is the probability that our first success should occur on the fourth or later? On the fourth trial or later. So what we want is to sum this sequence. It's a sequence of probability values, infinity long, and it's going to take us a while to do that. So I actually don't really want to do that. That's too much trouble. What I'm going to do is I'm going to realize that the sum total of this sample space, all the probabilities, must equal 1. So I'm going to take 1 and subtract out that portion of the sample space that I do not want, which is the probability of 1, plus the probability of 2 trials, plus the probability of 3 trials. Those are the ones that I don't want. So I'm gonna figure them out, I'm gonna add them up, and then I'm gonna subtract them from 1. This shouldn't be too difficult. Let me go ahead and do that. By the way, if you're thinking to yourself, well, what would happen if we did it the other way? I mean, I won't add up probability values all the way to infinity, but what happens if I just go kind of far and I add up the probability of 4 and 5 and 6 and so on? How close can I get, reasonably speaking? And the truth is, you can actually get pretty close that way. As it happens, and you know what, I really wish somebody would check this and make sure I'm not mistaken, but as it happens, the probability that the first success would happen on the 14th trial is less than, I think it would be the 14th trial, would be less than 1 in a million. So you're going to get really darn close with a reasonable amount of effort pretty fast. But close isn't good enough for us. We're going to get an exact value, and here's how we're going to do that. I'm going to take the probability of my unwanted cases, the probability of 1, which would equal the probability of failure to the power of the value, the number I'm evaluating, the number of trials I'm evaluating, minus 1 times the probability of success. And remember, anything, 1/3 anyway to the power of 0 is going to be 1. And so we have 1 times 2/3, which is 2/3. We have the probability that it would occur on the second trial, 1/3 to the power of 2 minus 1 times 2/3. And that's going to be 2/9. And then finally, right down here at the bottom, the probability that it would occur on the third trial would be 1/3 to the 3 minus 1 times 2/3. And that's going to be equal to 2/27. Good. Now let me just convert all of these fractions to 27ths. We're going to have 18 27ths, 6 27ths, and then 2 27ths. So I've got to add those all together and subtract from 1. Let me go ahead and do that. So 1 minus 18 27ths plus 6 27ths plus 2 27ths is, that's going to be equal to 27 27ths, that's the number 1, minus 26 27ths. And so here's my answer, 1/27. And that's going to be the probability that your first success with this funny coin would occur on the 4th trial or later. So I'm glad that that answered your questions. I hope it did anyway. Go ahead and make a comment if you didn't understand something or you want me to clarify something. And thanks a lot. I'll see you next time.